All right, I am so delighted to be here. I think we have a great program for you in this SFI Network Science short course. So my goal here is to give you a little bit of an overview of what's coming and then give you an introduction to network science. But before I begin, I would like to say a little bit about the types of systems that we're thinking about. So networks are everywhere. In a lot of social systems, biological systems, technological systems. A lot of times it's really useful to represent those systems as a network, a set of components and their interactions. So, and this is useful in a lot of different contexts, and sometimes these networks are physical, hardwired networks, like the internet, where you have computers connected by edges if they can pass information back and forth. A neural network is another example of a physical hardwired network where our nodes are neurons and they're connected by synapses. But then other times, a network is just a really useful way to represent complicated data. So social networks are like that. So we can think about Facebook, where the nodes are individuals and they're connected by friendships. And in biological systems, we can learn a lot about how the human body processes information and responds to external perturbations and different environmental conditions by drawing different kinds of networks of the interactions within the human body. So a metabolic network is an example. Here, the nodes are chemicals, and two chemicals would be connected by a link if they participate in a reaction together. But then there are a lot of systems that aren't really networks that you can kind of turn into a network problem, but you'd sort of almost artificially be doing that. So for instance, if I want to learn about the distribution of height in a population, I could measure everybody's height and draw an edge between two people if their height was similar within an inch, right? And I get a network out of that. But the network isn't really essential to the system or to the question that I'm asking. I'm just asking, well, what's the distribution of heights? So the important thing that I want to keep in mind, and then we'll talk about a little bit about later, is that a network approach is really appropriate when the role of a node, one of the components, or one of the links in a system really depends on the structure of connections throughout the entire system. Right? So if you're thinking about your business network, the reason we call this a network is because your ability to do business with someone might depend very much on who you know and who they know. And so your relatedness to the CEO of Goldman Sachs, for instance, depends on who they know and who you know, and do you have people that you know in common. So those are the cases where a network approach is really important. All right, so a little overview of this short course. Today, we're going to talk about network basics and how we can take data and look at it through the lens of network science. So I'm going to open with an introduction to network science, talking about how this field has grown and some of the early work and how it's useful to a lot of different real-world applications. And then we have Hernan Maxey, who will be our next speaker from the City College of New York, who's going to talk about some of those applications. Specifically, how do you look at the network structure of a system and find those influencers who are best able to maximize spread in a system? And then every day, we'll have a series of talks in the morning, and then lunch, and then a panel session with the morning speakers. And in that panel session, we'll have a little bit of a chance to talk about the types of systems that you're interested in. So for instance, today, one of the things that we'll ask of you is to tell us about the types of systems that you might think about that you think could be amenable to this network analysis that we'll talk about this morning. And we'll ask our panelists, okay, well, how would you approach that problem? What is the first type? What are the first things you would do? And so every day we have the morning lectures, a panel session where you guys really get to ask the speakers some more about the things that you're interested in. And then that's followed by a hands-on activity. So David Darman, in the back of the room, is running the hands-on activities. And so for those, what we're going to do is have you download software and really interact with some different data sets and get the feel for how you can kind of get started with network analysis. And maybe that you can take this away from this short program so you have tools. And you know, even if you don't think you're going to be able to redo these hands-on activities with your own data, at least you'll get a feel for how this is done. And if you're interested, you'll think, oh, I know what kind of person I need to hire to work on this type of project. So that's kind of our goal. So today is the basics, and then we'll talk about network dynamics tomorrow with 3 different speakers. Damon Santola from the University of Pennsylvania will talk about diffusion dynamics. Neo Martinez will talk about ecological networks, and Bill Rand will talk about agent-based network models. So on the second day, we're really thinking about processes on networks and how the connectivity pattern influences what we see happening in those processes. And the hands-on activity is building a network diffusion model. And so day 3, we're really kind of moving towards some more sophisticated network science tools, some more recent types of tools that have been developed, and some of the harder questions that we really haven't yet fully answered within the field of network science. Oh, this was repeated. Oh, anyway. Ignore these names here, I'll just tell you who they are. So we have Ole Peters, who's going to talk about cooperation networks. And then we have Peter Dodd, so this is all in your schedule, who will talk about big data-driven network science. And finally, we'll Daniel Larimore, who will talk about multi-layer networks. So even more complicated than the simple network representations that we'll talk about today. And David Darman will lead us in complex network visualization. But this morning, I just want to give you a feel for this network approach to looking at data. And so my goal here is to provide an introduction to this field of network science. And I'm going to start with some of these key early results from network science that are pretty useful for analyzing lots of different types of data. And not only analyzing that data, but just it provides a different perspective for thinking about this data than, you know, one might have had if you're just saying, okay, I want to do a statistical analysis of this data. So I want to give you a feel for what network science offers and when it might be useful. So I'm going to begin by talking about the types of systems we study. I already did that just a little bit, but I'll go into that a little bit more, and the questions that we're interested in. And then we'll talk about these measures, these network measures. You have a system, it's a network. What do you want to calculate on it? Where's a good place to start? And we don't only want to take a network and calculate these measures, we also need some way of figuring out, okay, well, I have this clustering coefficient. I calculated it for my network. What does it mean? What value is actually meaningful? Is this a high value of 0.3 or is that a low value? So we're going to talk about the network models that help us understand what these network measures mean. And then I'll do a little bit at the end, and actually I might not get to this part much, connecting structure to function, because there's more to come tomorrow, and some of it Hernan will talk about in the next lecture. All right. So there's a bunch of references. I've included just a few here. Let me tell you about these. This book is by Santa Fe Institute external professor Mark Newman. It's the complete guide to network science, but it's really written for a technical audience. This third one is also a pretty full guide to network science. It has a lot of technical pieces, but you can read a lot of it and skip the technical pieces and still get a lot of the messages, and it's available online. So if I think it's like bearbossy.org or bearbossy.net. So if you just search Bearbossy and network science book, I think this is a really good place to start for this audience. Although this first one, as an academic is my preference and is really complete. And then I also threw in this other book, which is an excellent book by David Easley and John Kleinberg. They're computer scientists. So if you have more of a computational bent, this is aimed at undergraduate computer scientists. So it's a bit technical, but it sort of asks questions from a bit of a different perspective than these other two. So the first one is a bit mathematical. This last one I think is the most general one. So you might want to consider those. And also, we will have all these slides available for you. And so I'll work that out with Will and Casey. Okay, so back to this question. I already started talking about networks, but I didn't explicitly define what a network is. So a network is a collection of nodes and links. Some people will call the nodes vertices, some people will call the links edges. I usually always use the word nodes, but I'll sometimes say edges instead of links, just so you know. So here are some different systems, some examples, and the nodes and links that are part of the network that comprises that system, composes that system. Okay, so the World Wide Web. The nodes are web pages, and the links are hyperlinks. So one web page has a hyperlink to another. So this is a directed network. A lot of the networks that I'm going to talk about are undirected. There's just a relationship between two nodes, and it doesn't go one way or the other. The World Wide Web is a specifically directed network. The internet, I mentioned that one earlier. The nodes are computers. The links are these IP links. Citation networks. This comes up in a lot of different contexts, things like this. It's actually quite like the World Wide Web. So here the nodes are papers and the links are citations. You can think of Supreme Court citation networks where the nodes are cases and the links are citations between cases. Social network, we talked about that before. The nodes can be individuals, they can be friendship, the links can be friendships, business relationships. You can classify the links in different ways. There are transportation networks, such as the subway or the metro, where the nodes are stations and the links are tracks. Biological networks, the example I showed you earlier was the neuronal network, where the nodes are neurons and the links are synapses. So there's lots of different kind of data that we can learn a lot from if we represent it this way as a network. But the first thing we need to do is define, well, what are our nodes and what are our links? So what kind of tools, so once we define what our nodes and links are, what kind of tools are we drawing from to do this type of network analysis? Well, we're drawing from a lot of different kinds of tools. So graph theory from mathematics. I'm a physicist, and our other morning speaker, Hernan, is also a physicist. A lot of physicists interested in this network science field, dynamical systems, social network theory. People have been thinking about social networks for a long time. Computer science, as I mentioned that book early on, that's kind of computer scientist approach to networks. And then complex systems, which is really the bread and butter of the Santa Fe Institute, which the aim of complex systems is to try to find commonalities for studying these really complicated systems. So you guys here are from different worlds in some sense, much more industry than the types of crowds that I usually speak up to, but you have different problems that you're interested in, different motivations for coming to this course, but we believe that a lot of these tools can be helpful in those different contexts. So at Santa Fe Institute, what we're trying to do is kind of find that underlying commonality that can explain the complexities that arise in a lot of different systems. Okay, so people obviously have been thinking about networks for a long time. I would say the field of network science is about 20 years old. So what's new about a network science approach compared to how people have been thinking about these exact same systems before network science came along. So there are these traditional questions. So in social networks, people have been thinking about this for a long time in sociology. But mostly the early work in social networks was focused on what I would say is small data, survey-driven interaction patterns between individuals. They might take a set of school children and ask them about their friendship and ask a question like, who is the most influential person in this small network? On the other side of things, graph theory has been asking questions for a really long time also. So you can have a graph, usually a small one, maybe a little bit bigger, but the mathematicians are interested in very provable features about this network. So like, does there exist a cycle through the network that uses each edge exactly once? This is the famous Konigsberg bridge problem, that cycle being an Eulerian circuit. In network science, and especially where network science meets data science, we're interested in more statistical questions about the overall patterns in the system. And we're usually interested in pretty large systems. How can we apply these tools to large systems where these types of things don't necessarily scale well when all of a sudden you have millions of nodes? So the network science type questions might be things like, how do different network structures influence the system's robustness to node or edge removal? So if I want to attack this system and I want to break it apart, how does that pattern of connectivity influence what strategy I use to break it apart and which nodes I choose to break it apart? And then, or similarly, how does the network structure influence the system's dynamics or function? So for a certain function, maybe there are certain kinds of network structures that are most important to that type of function. Those are the things that we think about in network science. So network science, I would say, can be divided into this dichotomy of structural complexity and dynamical complexity. And then at the higher level, we can have both structural and dynamical complexity. Today, we're going to focus mostly on structure. Tomorrow, we're going to focus on dynamics. And on the third day, we're kind of going to focus on even harder questions than some of these things. So structural complexity, I'm really just looking at the pattern of interactions and trying to characterize that pattern. So this pattern could have very complex features, and it could be far from perfectly regular. So perfectly regular is like a grid. Manhattan, if you think of the streets of Manhattan, you think of the nodes as intersections and the streets as links between intersections. That's a really regular network. And that's something that's pretty easy to analyze. Perfectly random, if we draw all the connections randomly, that's also pretty easy to analyze and understand. But it's these networks that are far from either of those two extremes that need these more complicated approaches that we're going to develop. And so we could have this intricate wiring pattern, but also, so far I'm just assuming there's nodes and there's links. There's one kind of node and one kind of link, but we can have different kinds of nodes. In a business, for instance, you might have managers, you might have the CEO. Those people don't have the same role in the system. You could have lawyers and economists in a certain agency. So and they could have different rules for interaction. In addition, the edges could be heterogeneous with different weights, directions, and signs. So there might be some people that you're much closer friends to. So we don't want to say, we just don't want a binary question, are two people friends or not? We might want to quantify the strength of that relationship. There also could be different types of relationships. Like if I talk about the social network, you might think about your friends outside of work, and that would have a different character to you than your work relationships. And then there could be different signs, right? So a teenager might want to do the opposite of what their parents do, whereas most other friendships might indicate some kind of similarity between the individuals. And then Beyond the structural complexity, we have the dynamical complexity, which will be the focus of tomorrow. We can have dynamics on the network, processes taking place on a fixed network. So if we think about the spread of disease through a population, we could approximate the social network as fixed, and then disease spreads, like the flu, spreads over this social network. We can think about dynamics of the network. The network itself could be evolving in time. This could be, for instance, the development of the brain from the fetus stage through early childhood and beyond. Your network of neurons changes dramatically in those times. But we can also have dynamics happening on the network and the network changing at the same time. So the first example I gave is actually a good one of that. So the spread of disease, right? When we have the flu, we actually change our social networks. We stay home more, and also some people will go to hospitals. And that really changes the profile of how things spread. So those processes happening together are things that we're interested in. Okay. So let's get started in, well, how do we first analyze some of these systems? So first we have nodes and edges. Let's first assume that all the nodes are binary. They exist or they don't. So I'm going to first represent the network with an adjacency matrix. So it's just a matrix where the elements of the matrix A sub ij, so the connection between node I and node j is going to be 1 if there's a link from I to j and 0 otherwise. So here's this tiny little network, which is undirected, which means that aij equals aj. So it's symmetric. If I go down this diagonal here, I have a mirror image of the top upper triangular part with the bottom lower triangular part. But sometimes, as I talked to earlier in the citation networks, the networks are actually directed so here node 1 is connected to nodes 2 and 3. So node 1 is represented by this first row here. Node 2 is connected to node 4. Node 3 has no outgoing connections. And node 4 is connected to node 3. So this is kind of one of the simplest ways that we often choose to represent a network. However, it's pretty costly. So I talked earlier about some of the early work examining networks was on small networks. And you can store these adjacency matrices if your networks are 30, 100, 1,000. That's fine. But a lot of the data that we're interested in, there could be millions or billions of nodes. If you're interested in the relationship between stocks, or if you want to capture trades and things like that. And so in those cases, usually these networks have a lot of zeros in them. So if you think about friendship networks, for example, you think about everybody on Facebook, and people have maybe on average in a few hundreds of Facebook connections, but most of if you look at through all the Facebook users, you don't have a connection to the vast majority of them. So if you were to store this matrix, it would be almost all zeros. So we don't want to do that. We want to avoid that. So we can think about other representations. An edge list, for example. So here, we just write down the pairs of nodes that are connected by edges. And here, I've chosen the convention that so there's an edge between 1 and 2. I could have written it as 2, 1 also. I choose the convention that I write it down once with the lower numbered node listed first. And in the directed network, I'm no longer making that assumption that the relationship is bidirectional. So here I have an edge that points from node 4 to node 3. And it wouldn't be equivalent for me to list that as 3, 4. So this is a very compact representation. I've just written down all my edges, but it's not that easy to use, because if I want to ask here, for instance, well, what are all the nodes that are connected to node 3, I have to search through this list. And I don't know exactly where those are going to be found. So what we do usually is represent these networks as what's called an adjacency list. This comes under different names. But basically, I have a row that is going to list the connections of each node. So row 1 is the connections of node 1, row 2 of node 2, and so on. And that makes it very easy for me to look up this information, right? And so it looks like, okay, well, there's basically the same information here as over here, but this is much easier to look up. And then you notice that in this directed case, the lengths of each row aren't going to be the same. Some nodes are going to have many, many connections, possibly, and some nodes will have fewer connections. But this is a good way, in general, for us to represent this kind of data. So just things to keep in mind. Okay, so once we represent this data, one of the things we might want to ask, so I have this network, this data, I put it into this format, and now I want to ask questions, what kind of structure does it have? But I want to know, I'll want to know, how do I know if these structures are significant? So the first thing that we tend to compare it to is a random graph. What if all the connections were random? And so that brings us to this notion of Erdős-Rényi random graphs. So if I have a system of n nodes, if my real data has n nodes and m edges, I'm going to make a random graph that kind of has that has the exact same number of nodes and maybe the same average number of edges. And there's a few different ways I can do this. But one of the classic ways is to consider the system of n nodes, and I can connect each pair of nodes with a small probability. If I desire m edges total, and let's say m is this number taken from my data, and n is also taken from my data, then I set this value of p to be 2m over n times n minus 1. So it's the n minus 1 over 2 is the number of pairs of nodes in the system, and m is the number of edges. So the fraction of pairs of nodes that are connected by edges is this probability. And then I go through for each pair of nodes. So let's say I start with this node, I look at every other node. For each pair of nodes, I flip a coin. If that coin flip says that I should connect them, then I do so. So here, these are 3 different network realizations. I have 10 nodes, and my probability of connecting any pair of edges is a 6th here. And I do this a few times. I get 7 edges one time, I get 8 edges another time, I get 9 edges another time. But these are different networks that have completely random structure that I've created. Now, you might notice that if I do it this way, where I connect each pair with a fixed probability, I might want a certain number of edges. So I might have wanted 8 edges here, but I won't get exactly 8 edges in this process. You could say, I want exactly 8 edges of these pairs of nodes. I'm going to choose exactly 8 of those. So this model that I showed you here is called the G for graph, N, P model, where P is the probability. But there's also a similar model, G, N, M, where I fix the number of edges. So those are just 2 different randomizations you can think about. But what I really want to drive home is the utility of this is you have this data set and you want to compare what it looks like to a random graph with the same number of nodes and about the same number of edges. Okay, so what are some things we might start to calculate on this graph? One thing that people were interested in early on and is just are things like average path lengths. So I'm going to look at every pair of nodes, I and j, in the system, and I want to find, let dij be the number of edges in the shortest path between nodes I and j. And then I just calculate, well, what is the average of that value? So if I go back here, right, I look at every single pair of nodes. Let's say if I look at this node and this node here, well, if I want to find the shortest path to it, let's see, we could go here and then here. So 1, 2, 3, 4. Oh, there is no path between these two in this network. Okay, so let me take this one and this one here. Okay, so the top one and this bottom one here. So the path is, oh, I keep taking the wrong ones. Let's see. Oh yeah, 1, 2, 3, 4, 5, 6. So the path is of length 6. So I do that for every single pair. I calculate, well, what's the average of that? And that gives me my average path length. I could also keep all of those values and get the distribution of path lengths. Yes?
Michelle, if the two are not connected, what is the path length?
So we would call it infinity. So in general, when you're doing this, you would calculate it only for the component where everything is connected. You take the largest connected component where there's a path from one node to everything else, and then you would calculate this. Another thing that you can do, if you have lots of situations where there are many pairs of nodes that are not connected, you can calculate, instead of a geometric mean, what we call the harmonic mean. So you can calculate the average of 1 over the distance, right? So if they're not connected, that value is 1 over infinity, so that's 0. So then that's a well-defined calculation. So if you're really interested in a system where you have lots of nodes that are not connected to each other, you might want to think about the harmonic mean instead of this. Okay. So another thing we might think about is what's called clustering, or you could also think about it as transitivity. So it's the probability that 2 of a node's neighbors are themselves connected. So I take a node, I know that it has connections to these 2 other nodes, the green nodes here. And I want to say, if I look at all such triads, a blue node connected to 2 green nodes, what's the probability that the green nodes are themselves connected? And in an Erdos-Rényi graph, this probability, okay, so let's say I take an Erdos-Rényi graph. Let me go back. Okay, I'm going to take an Erdos-Rényi graph, and I have a number of nodes n, and the mean degree, the average number of edges connected to a node, that's going to be 2m over n, right? So I'm going to say that n, the number of nodes, I'm going to consider systems with larger and larger numbers of nodes. So a network with 100 nodes, a network with 1,000 nodes, a network with 10,000 nodes, and so on. But all the while, I'm going to say, okay, I'm going to think about this Erdos-Rényi network, but I'm going to say all the time the average number of connections per node is 5. So it gets bigger and bigger. The number of nodes gets bigger, but the average number of connections stays the same. So in that case, if I have these Erdos-Rényi networks, and I calculate this clustering coefficient, the clustering coefficient for a random graph where the average degree is held constant is going to be like 1 over n. So it's going to get smaller and smaller as I add more and more nodes to the system, always under the constraint that everybody has about the same number of connections, even as the system gets bigger and bigger, which is a reasonable approximation for lots of different types of networks. And in fact, almost all the data that we look at, if you look at bigger and bigger networks, the average degree stays relatively constant. So the average degree is not getting bigger with the network size for most of the types of networks that we think about. That's the condition of what we call sparsity. Okay. So here, this is the calculated cluster clustering coefficient for a few different networks. So here is the network of movie actors. So if you've heard about this 6 degrees of Kevin Bacon game. So here the nodes are actors. 2 actors are connected by an edge if they acted in a movie together. The number of nodes is listed here, over 200,000 in this database. The average path length is just under 4. The clustering coefficient for this network is 0.79, which sounds big as it is, but it sounds even bigger when you realize, okay, what do we compare it to? The clustering coefficient for a random network with the same number of nodes and edges. For a neural network, this is the neural network of the nematode C. elegans, a little worm. The number of nodes is small. The average path length is a little under 3. The clustering coefficient is about 0.3, which is still much larger than the clustering coefficient in a random graph of 0.05. And in this power grid network, this is the power grid of the Western US and Canada, about 5,000 nodes, bigger average path length of about 20, clustering coefficient of 0.08, which is really still a couple orders of magnitude bigger than the clustering coefficient of the equivalent random graph. So that's where what I want to talk about. So network models, null models, as we would often think of them, we need these null models to evaluate the significance of these values that we calculate, these network statistics that we calculate on the data, to tell us how meaningful they might be, how surprising they might be. But we'll talk a little bit later about somewhat more sophisticated null models. Okay, now so I was talking about null models. The Erdős-Rényi random graph is a null model. I have data and I want to say, well, how does this compare to a network that's perfectly random? There are other network models that we think about to kind of explain the structure that we see in network data. And those I'm going to call generative models. So they're not for comparison's sake, but rather to show, perhaps in a mechanistic way, but in a generative way, how we can get through a model the features that we see in data. So this is the paper that I feel kicked off the field of network science. So this is a paper by Duncan Watts and Steve Strogatz, Collective Dynamics of Small World Networks, that appeared in Nature in 1998. So what Duncan and Steve were interested in was this question, well, if you think about networks and you think about clustering and path length, right? It's easy if you have a really structured grid-like network, right? Let's say everybody lives on a grid and they kind of connect to the people close to them on the grid, like in Manhattan. It's easy to have very high clustering, triangle closure in that type of network, but your average path length would get pretty big if, as this grid size got bigger and bigger. Your average path length would be pretty long. Now, if you connected everybody randomly, like in that Erdős-Rényi network, your average path length is really going to be very short. But your clustering coefficient, as we saw in that last table, for a random graph is also going to be very low. Now, in real social networks, we have both high clustering coefficients and short path lengths at the same time. So what this model does is explain to us how we can get that pretty easily. We don't need a lot of ingredients to make that happen. So what they did was they tuned from a regular graph. So here they're imagining that everybody lives on a line and they're connected to their k nearest neighbors on either side. So actually it's a circle. So everybody lives on a big circle and you're connected to the people nearby on that circle on either side. And then what they did was they tuned this probability for each. So they started with this regular lattice, and then they tuned the probability of rewiring every edge. So for p equals 0.1, they looked at every edge, they flipped a coin, and they rewired that edge with that small 10% probability. They picked one of the ends at random and moved it somewhere else. So you get this intermediate structure, which is what they were calling small worlds, that has this strong local structure still, but also some long-range connections. So you can think about that as, well, most people are kind of constrained in their social networks to their local neighborhoods, but you have a few people who have these really long-range connections, these jet setters maybe. And then as you tune this probability of rewiring to 1, then you get basically an Erdős-Rényi network when you're rewiring all the edges. And so what they showed was, as a function of this rewiring probability, notice this is on a logarithmic scale. So here, this is p equals 0.001, 0.01, 0.1, and 1. So you have this big range. Okay, so this top curve with the open squares is the clustering coefficient at this level of p divided by what its value when p equals 0. So here, at p equals 0, you have high clustering, and then you keep having high clustering for quite some time, but your path length, as you increase this rewiring probability, drops much sooner. So you get this big range over which you can have both highly local social network structure, where we have this high clustering, but also all the advantages of the random network, where you have short path length. So this was like an explanatory model of some of the features that we see in real-world networks. So that first paper asked the question, how can I explain the clustering and the path lengths patterns that we see in real-world networks with a simple model? The next thing that we're interested in this field of network science actually came from Laszlo Barabasi and Reka Albert, where they said, well, there's something else that really distinguishes different networks. If I just want to look at a few properties of networks, one thing I might want to look at is this degree distribution. So the degree of the node is the number of connections that it has to other nodes. And in this Erdős-Rényi network, if I make the network, as I said, I have a fixed number of nodes and a fixed probability of connecting every pair, I get a sharply peaked degree distribution. So the probability that a node has a certain degree is sharply peaked around some value, and there's a little bit of spread in it, but not a lot. And some real-world networks have that feature, like if we look at road networks, they have this sharply peaked distribution. But there's a whole other class of networks that are almost what we would call a scale-free, or maybe more accurately, highly skewed networks. So this is the network of airline flights. So the nodes are airports. 2 airports are connected by an edge if there's a flight from one to another. And it has a structure that most airports are small. Right? If you listed all the airports, most of them are really small. They don't have a lot of flights out of them. But there are a few hubs, like Newark, like JFK, like Atlanta, like Dulles in DC, that have very large degrees. So if you were to draw this degree distribution, the probability of having a given degree, it's actually quite high for low degrees, and it's small, but not insignificant for much higher degrees. So one thing that we often do is we plot these things on a log-log scale, right? So if I were to plot this sharply peaked distribution on a log-log scale, this turns over pretty quickly, right? And if you look at, well, what's this probability of having something around size 100? This is tiny, 1 times 10 to the minus 64. But if you do it on this scale, these scale-free or power law tail distributions, you get a straight line on a log-log scale, and you see that the probability of having something pretty big, it's small, but it's not minuscule, right? So you still have these airports that have a huge number of connections versus on the road network, you never see a road, an intersection that has 100 roads coming into it. And so this is an important thing to look at in your data that really characterizes the data. So if we look look at the degree distributions for various networks. This is from an early review article by Strogatz. Early, the field started in 1988, and this was in 2001. But what you see is that networks are really different in this property. So here's the World Wide Web. This is the probability or the frequency, the number of web pages that have this in degree. I'm plotting this on that log scale. So this is one of those heavy-tailed distributions. So here, I'm all the way out to 10,000, and I have kind of a significant number of web pages that have 10,000 incoming links to them. So it's a directed network, so I could plot it versus in degree or out degree. So in degree is what we'd be interested in these World Wide Web. How many web pages point to this one? And then there are some others. So this is a co-authorship network. So the individuals are scientists. They're connected by an edge if they've written a paper. And you see that this, it looks like a straight line for a little bit and then it turns over. One of the things is, there's basically no cost to a website for getting more and more hyperlinks. CNN doesn't notice if you link to CNN. But for these people, there might be some scientists who are way more productive than others and way more collaborative than others, but there's sort of a fixed limit on how many papers can they actually write. So in that case, you would expect this to turn over eventually. But then some networks don't have this heavy tail. So here, this is the distribution for the power grid of the Western US and Canada. And here, this is on a linear scale instead of a logarithmic scale on the x-axis. So this one goes out to 10,000. This one only goes out to 20. So this is going to be this kind of more quickly decaying distribution. Same with this social network here. Okay, so back to explanatory or generative models. So some of this early work, one of the interesting things here was asking the question, where do these power law degree distributions come from? We see these scale-free degree distributions where some nodes, or like the airline hubs, have huge number of connections and others have, but most have just small number of connections. How can we explain that mechanistically? So this was this really influential paper by Baerbock and Albert in Science in 1999, and their answer was preferential attachment. So they start with a network. They start with a small network, some kind of seed network, and it doesn't really matter what the structure of that small network is. But at each time step, they're going to add a new node, like this node here, and it's going to have n new edges. So it's this one, in this case, n is 2. I'm going to connect to 2 nodes that already exist in the system. But I'm not going to connect randomly to 2 nodes that already exist. I'm going to connect preferentially, such that the probability that a new node connects to an existing node depends on the connectivity at that time point of the existing nodes. So the idea here is, let's say I'm writing a web page. I'm more likely to add hyperlinks to web pages that already have a lot of hyperlinks. In fact, my probability for doing so in this model is just proportional to the number of hyperlinks they already have. And if I keep growing this process, I get out one of these scale-free degree distributions. So here's a generative model that offers one mechanism for how these scale-free degree distributions might arise. Okay. How do these degree distributions matter? So let's think about this in a really simple example, sort of just showing how the mathematics behind networks can be important. So I'm going to consider 2 networks. So first, I'm going to have network 1 that has 105 people, and everyone has exactly 8 friends. Network 2 has 105 people, but there are 2 classes of people in this case. I have 100 regular folk, and each of them have 5 friends. But I have, in addition to those, 5 bigwigs. But each of these bigwigs have 60 regular folk friends. And all the bigwigs are friends with each other. So here, I have this uniform degree distribution in network 1. Everyone has the same number of friends. But I have this 2-class degree distribution in network 2 that I have these regular folks. Most of the system is regular folks that have 5 friends, but then I have these 5 bigwigs where they have 60 regular friends. The average number of friends in my network 2 is just under 8, so kind of similar to network 1. So the averages are the same, but then there are other features that are going to be really different. So for instance, we can ask, how many friends do your friends have on average? So what do I mean kind of mathematically when I ask that question? I want to pick a random person, and I want to pick a random one of their friends and say, how many friends does that person have? And so in network 1, it's easy because everyone has exactly 8 friends. So that number is 8. In network 2, I'm going to do this process, and this number is going to end up being much, much larger. The average number of friends of your friends is really high. It's 40. And so that's important in understanding lots of things in networks, right? So for instance, as I explain this to you, it might make sense. So there's some of you nodding, okay, that makes sense. But there are a lot of times where let's say on Facebook, right? I look at my friends on Facebook, I look at how many friends they have on average. I expect my friends to be kind of chosen randomly. They should have about the same number of friends as I do. And then I feel really bad that they have so many more friends than I do. But I shouldn't feel really bad because that's to be expected. Your friends are way more popular than you on average, and that's because you're way more likely to be connected to popular people. So let's think about one way in which we could draw this network too. So I have this graph where if you have 100 regular folk and each of them have 5 friends, in order to fulfill this condition where the 5 bigwigs each have 60 regular folk friends, you're going to have, on average, these 100 regular folk friends, 3 of their friends are going to be bigwigs. And so that's how you get this average number of friends of your friends to be 40. So this is just one example about how we might want to think about the explicit details of the network math and not just our intuition, where we're thinking that a friend of a friend is just like choosing a person at random, has the same profile as a person chosen at random. No, the statistics are different. If I pick a person at random in this network, their average number of friends is close to 8. If I pick a person, a friend of a friend, their average number of friends is going to be 40. It's because that second person I didn't pick at random. I picked that person by following a randomly chosen link. And the people who have high degree have lots more links connected to them. All right. Okay, so so I talked about degree, but there are other features that are really important in networks, and so what we might call higher order features. So one thing I want to talk about is assortative mixing. So in assortatively mixed networks, like vertices tend to connect preferentially to one another. And so you can have assortative mixing by discrete traits, discrete or continuous traits. So here's an example. This is a friendship network of students in a US school, and these nodes are color-coded according to race. So you see that there are a lot more connections between white students, and there are a lot of connections from black students to other black students, and the connections between white and black students are relatively less dense. This is actually drawn with a layout algorithm, a not so sophisticated layout algorithm that basically tries to draw groups of nodes together if there's a lot of connections between them. So you see that there's actually 4 groups here. So what's interesting is you see these 4 groups, there's this divide along this diagonal here according to race, where students are more likely to connect to other students of the same race, but there's also a divide along this diagonal, and that actually is according to age. Students are more likely to connect to it. So these are high school students, and these are junior high school students. And so this is assortative mixing, an example according to two different traits, race and age. But we also have assortative mixing by degree. And that happens if high degree vertices tend to connect preferentially to other high degree vertices. So I look at what would happen if everything were random, constraining on a degree distribution, and I say, well, actually, these power players connect to each other even more than you would expect, given that they have these high degrees. That's assortatively mixed. So a network is disassortatively mixed if high degree vertices tend to connect preferentially to low degree vertices. So these are two different networks that have the same degree distribution, but different degree correlations, different levels of assortativity. So here the high degree nodes tend to connect preferentially to one another, and here the high degree nodes like to connect to the low degree nodes. And you see you get dramatically different structures. Here you have this central core that's kind of dominated by these bigwigs. And here you have a more distributed system where you have these hub nodes, but they kind of spread out from one another, they fan out. And we can measure the assortativity by this assortativity coefficient, which is just this Pearson correlation of the excess degree of nodes. So I look at all the edges, and for every edge, I know the degree of the nodes at the end of that edge. But I want the excess degree, because I have this edge that I consider, and I want to say, okay, there's node A and node B. At the end of these edges, what's the degree of node A, not including this edge? What's the degree of node B, not including that edge? What's the correlation coefficient of those values? And that gives me the assortative mixing. So it's a number between -1 and 1. 1 if these vertices like to connect to other vertices of the same degree, of similar degree. So here's some measured assortativity values from various networks. It turns out that social networks tend to have high positive values of assortativity. Popular people like to connect preferentially to other popular people. But that's not true in technological and biological networks. And there could be systemic reasons for constructing those networks so that they're actually pretty strongly disassortative. So that's one big difference, something you can measure about a network that really helps characterize it and influences properties of that network, like its resilience to attack. Okay, so I had degree correlations. Some other things that I could look at are what we call network motifs, little subgraphs. So I've already thought about this once when we talked about clustering. That clustering coefficient relates to the network's propensity for having lots of triangles in it. But I could, if I'm in a directed network, I might not just be interested in triangle, or I have to think about the direction of those edges. So I want to look at a motif is going to be defined as a subgraph that has significantly higher density in the observed network than in randomizations of the same. And I'm going to talk about these randomizations in the next slide. So this is going to be a little bit more sophisticated null model than the Erdos-Renyi null model I talked about before. So what are these subgraphs? So here, this is what we call a feed-forward loop. X influences Y, Y influences Z, and X also influences Z. And so if you look at these, what they do is they count up in the data, you take your data set, you count up all these realizations. How many motifs does it have? Here it has the gene regulatory network for the bacterium E. coli has 40 of these feed-forward loops. For yeast, it has 70. And if you compare that to the null model, that's pretty significant. The null model for E. coli only has 7, and we can have some sort of standard deviation on that. So similarly, this feed-forward loop is important in neurons. That comes up, well, we see a lot of those in food webs. This structure, this linear structure, X influences Y, actually X eats Y, Y eats Z, is a really important one that happens much more than you would expect given your null model. So this is something else a little bit harder to calculate. There's all these software packages that calculate these things, but if you're looking through your data and you're saying, okay, well, how do I characterize it? This might be a next level thing to look at. But in doing so, in order to assess this value, I count up these motifs, but I need to know how significant is this number of feed-forward loops that I've counted. So that's where I need a little bit more sophisticated null model. So that brings me to what we call the configuration model. So I said the degree was really important. And now what I want to ask is, what other structure do I have in this network, given that I have this specific degree distribution? So suppose we want to consider a network that has this specified degree distribution, the exact same as the data that we're looking at, but is otherwise random. So if I have this network, I can say, okay, well, how much of the features that I see in my data are really just coming from the degree distribution, and how much of it is from other higher order structure? So that's where I need this randomization, which is called the configuration model. And it's not too hard to generate, although there are some caveats. To generate these networks, so I have a degree sequence that lists the degree k sub I for each node I. So this is I get from my data. Node 1 has degree 5, node 2 has degree 6, node 3 has degree 1, and so on. So what I do is I put k sub I copies of each node I into a bin, right? So node 1 has degree 6. I put 6 balls that are labeled 1 into this bin. Node 2 has degree 5. I put 5 balls that are labeled 2 into this bin. And in order to make my random network, I'm going to draw pairs of nodes from the bin and connect them by edges. So I have this bin full of balls with different labels on them, and I'm drawing pairs. If I draw a 1 and a 7, that means I'm connecting 1 and 7 by an edge. And I'm going to repeat this process. And it works pretty well to generate a network that has this specified degree distribution, which is usually specified from the data, but is otherwise random. But there are some caveats. This process can generate double edges and self loops, and usually I might think of my data as not allowing double edges and self loops. So for instance, if I have really high degree nodes, so in this network 2 that I talked about earlier, where I had these bigwigs, they each had 60 connections, what would happen in this case would be likely that, let's say nodes 1 through 5 are the bigwigs, and they each have 60 connections. So I have 60 balls labeled number 1, 60 balls labeled 2, and so on. In this process of generating this random model, it's likely that I end up with multiple edges between bigwigs, and I kind of didn't want that to begin with. But usually what we do is we say, okay, I'm going to do this process. I'm going to at the end, I'll get rid of all the double edges and the self loops. The self loops mean that I'm drawing an edge between node 1 and itself, for example. I'm going to get rid of that, and I'm just going to call that my maximally random network with the same degree distribution, or I could do some more sophisticated things. But basically, the important thing is I've now had, instead of having the random network where I've just constrained the number of nodes and the number of edges, I'm now constraining the degree distribution. And so doing so, I can now evaluate the other structures in the network that aren't going to be explained just by the degree distribution. So one of these things that I've thought extensively about is this issue of community structure. So community structure exists when there are groups of nodes within which connections are relatively dense, but between the groups, the connections are much sparser. And we already saw an example of that. And I said, okay, this was drawn with a simple visual layout algorithm. But in fact, if I give you an arbitrary network with just the nodes and the edges, it can be really pretty hard to find that community structure. And so the challenge of community detection is as follows. Given an arbitrary network, we want to develop a method to divide the network into groups, or communities as we call them, such that the within group edges are relatively dense. And an important caveat is we don't want to specify the number of groups a priori. So here there are 4 groups, but maybe we didn't know that. We want to just be able to find what's the natural number of groups in the system. So one thing that we can do is quantify the strength, so we can consider all possible partitions of the network into all numbers of groups, right? And I can have some kind of objective function that quantifies the strength of a given partition of the network into k communities. And so that is this modularity function that I'll just talk very briefly about. But this is the basic idea. Lots of networks have these strong communities, and if I just did these configuration model networks, they wouldn't have this community structure. So that's why I needed that configuration model to evaluate, in some ways, the strength of these communities. Okay, so this one way, one sort of intuitive way to find communities was this early work that I did with Mark Newman, this betweenness-based method for detecting communities. So the idea here is I have these network measures that I can calculate for different nodes. So for different nodes, I have their degree. But there's another more sophisticated network measure that's going to be useful for me to build an intuitive method for calculating these communities. And that's this idea of betweenness. So here, our idea is that we have this network, we think it's divided into communities. And we can try to detect these communities by identifying the boundaries, those links that go between communities. And we can use these centrality measures, these simple network measures, to help identify those boundaries. So the idea here is that there's this concept of node betweenness. So we have different centrality measures that measure the importance of different nodes. So degree is one, that gives me the number of connections that node has. Another measure of node importance is what's called betweenness. So the betweenness centrality of a vertex I is the number of shortest paths between pairs of other vertices which run through I. So if I just pick a random node, now what I'm going to do is I'm going to look at all pairs of nodes in this system. And I'm going to count how many of those pairs had a shortest path that went through this node of interest. And that gives me the node betweenness. And so here, what's going to happen is that these nodes that are connected to edges, these red edges that link different communities, those are going to have higher betweenness because the shortest path from these green nodes to these blue nodes here, they're going to lie along these red edges. Because that's the only way. I mean, you could go through the yellow and then back this way. But in general, we'd expect these to lie along these 2 red edges. So we can also generalize this notion of node betweenness to a notion of edge betweenness to give me the importance of different edges in connecting groups of nodes. So the betweenness of an edge is the number of shortest paths between pairs of nodes which run along those edges. So these red edges in this simple toy network construction, those red edges are going to have really high betweenness compared to the black edges. So I can use that to build a method to detect community. So here's a simple algorithm that we came up with, and it's not the best algorithm. You can do a lot better nowadays, but it's an intuitive way to think about community structure, and we're really pleased that it kind of led to a lot of better algorithms for defining community structure. So what we can do is we can calculate the betweennesses for all edges in the network. And that's actually a little bit of a computationally intensive step because I had said we have to consider all shortest paths between all We have to consider the shortest path between all pairs of nodes. So we have to do this. It's not that easy, but it's not that hard. We have to remove the edge. So it's not that easy. It's not that hard if the network is, you know, in the thousands, tens of thousands. It gets really hard if we're in the millions of nodes. So we remove the edge with the highest betweenness, and then we recalculate all the betweennesses affected by the removal, and then we repeat from step 2 until no edges remain. So the idea here is if I have a network that's composed of 2 communities, if I take this and I remove the edge with the highest betweenness, that's going to have the effect, so if there are multiple paths between these 2 communities, it's going to be necessary that one of them has high betweenness, but not necessarily all of them. So if I didn't do this recalculation step, obviously I would remove this red edge first. That would have the highest betweenness. But it could be that one of these black edges might have the next highest betweenness. But if I do this recalculation step, once this red edge is removed, then these blue edges get much higher betweenness. The betweenness flow, as we say, that was along this red edge is now redirected to here. So this allows us to kind of iteratively decompose the network into smaller and smaller communities. And as I said, this is an intuitive way to use network measures to find communities, but now there are some more sophisticated ways, and I don't want to go into this. This is some work that we introduced in 2004, but the technical details are we can write down a function. And this function, as I mentioned very briefly before, quantifies the strength of a given partition into k communities and says, okay, for that partition, the modularity measures the observed within community density of links compared to the expected value, and this expected value is calculated using that configuration model. So I need my null model once again. And then what I can do is I can write an algorithm that wants to maximize this quantity. So maximizing this quantity perfectly is a really, really hard computational problem, but I can find many heuristic algorithms that run almost in linear time, linear in the number of nodes. So I can still do it for millions of nodes that finds me a partition of the network into communities that maximizes this function. So for any network, I can partition it into communities, but I want to be able to say, are these communities significant? And that's where that null model comes in. So far, I talked about some structural features. I talked about clustering and shortest paths and degree distributions, some higher order degree correlations, and community structure, which is more of a mesoscale structure. But I want to talk a little bit, at least, about how these structural features influence the function of these networks. So one of the simplest examples, and I think Hernan will talk about spreading processes in a lot more detail, is what we call percolation. So if we want to connect the structure of a network to dynamics, as physicists, we think about this problem that we call percolation. And so percolation is this idea that I have some kind of porous material, like a rock, right? And the rock has spaces in it. And percolation is I want to ask whether oil will percolate, comes from the problem of asking whether oil will percolate from one side of the rock to another. And we can model this in a very simple way. So the rock is this kind of simple structure. We can say, okay, well, let's use this grid-like model here. So a very simple network. And in my percolation problem, I consider either bond percolation or site percolation. So in bond percolation, I'm going to fill in each link with a certain probability. And when I fill in that link, that means there can be flow along that bond, right? And then I want to ask questions about, well, how big are these connected components where I can have flow within that component? And I can do the same thing in site percolation. So before Or we think about this as a network problem where we can think about the spread of information. Okay, well, why is this important? How does this relate to anything I've been saying so far? Well, I can turn this into a network problem, and I can think about bomb circulation on a network. That can be a useful model for thinking about the spread of disease on a network. Or site percolation. Let's say I want to immunize a certain fraction of my population against spreading. So that could be where site percolation comes in. So I'll talk a little bit more about this, but let's think about this percolation problem on the grid. So what happens as we increase this probability of filling in these bonds? So for low values of this probability, we see small islands of connected components. And as I increase that tuning parameter, x, I get larger and larger values of these. This here is the mean component size. This solid line is the mean component size excluding the biggest component. And at some critical value, I get this formation of a really big component. That's when we say the system percolates. So we get this transition. Below the transition, we have small components. Above the transition, we have this large giant component. That's this dashed line. That's the size of the giant component. And then if we're well above the transition, most everything is in the giant component. And if we look at the connected components that aren't connected to the biggest one, they're pretty small overall. So there's this phase transition. And this is going to be important to information spread, right? So if you're thinking about information spread in a system, and you think about this occupation probability as the probability that one person spreads information to another, there's going to be some critical value of that probability where we have this large-scale information spread. So that's how it relates to the systems that we've been thinking about so far. So I talked about bomb percolation and site percolation. On grids, we can think about these same problems on networks. So the network percolates when a really large connected component forms. And so simple models of disease spread, as I was saying, can be mapped onto this bond percolation, right? So bond percolation, where I fill in the bond if there's a transmission event between those two nodes. So not every link is going to be able to transmit the disease. But let's say I have this bomb percolation problem, and then I take only the subset where those links are filled in, and I look at it over here in terms of the site percolation problem, and I can ask myself, well, which nodes should I have vaccinated in order to stop this spread? And how does that vaccination strategy depend on the structure of